To conduct one-way ANOVA, go to Task and Utilities. Under Task, under My Task, under Linear Models, double-click on one-way ANOVA. Make sure that correct data set is selected, and then let's have our dependent variable be diastolic blood pressure, and a categorical variable we can choose between weight status and cholesterol status. Let's choose cholesterol status because it also has three categories. So in this case, we will be seeing if there is a statistically significant difference in the three cholesterol status categories when it comes to the mean diastolic blood pressure is concerned. Okay, so in the options tab, I'm going to keep all the default options. Only thing which I'm going to change is the maximum number of plot points. I will change it to no limits. To no limits. Okay, and I will submit the code. Okay, so here are our results. I'm gonna copy all of them and paste them in ChatGPT. I'm not even gonna, maybe I will ask them to give me the interpretation table by table. Give me the interpretation table by table. Control V, I have pasted all my results. Okay, let's see what ChatGPT gives us. Okay, so table 1, class level information, independent variables, cholesterol status, which has 3 levels, borderline, desirable, and high. Dependent variable, diastolic blood pressure. Sample size is 5,209 observations. 5,209 read and 5,557 were used. So we can see here that almost 150 or so rows were empty. They were missing data from there. So maybe the patients were, there can be multiple reasons why there are missing values. Maybe the patient was dead by then, or it was not checked at the time of this data collection point, or so on and so forth. Anyways, moving on, overall ANOVA. So this is the most important table of this test. We see that model we had 3 categories. So degrees of freedom will be 3 minus 1, that is 2 degrees of freedom, and total sum of squares, it is slightly going to be, of course, very, very complex, but the basic calculations of the model sum of squares will be the same that we saw in our last video. And when we divide this value by the total number of total degrees of freedom, we get this value. Same goes with the error sum of squares. This is the variability within the samples, which was 5,054. We know that these were total number of participants with the cholesterol status being provided was 5,057, but we subtracted 3 of them because of 3 groups. So we have 5,054 degrees of freedom, and the total variance within groups was this value. And if we divide this value by this value, we get 163. And the F statistics, as we saw in the previous lecture, will be calculated by dividing the model sum of squares with error sum of squares. That is the variability between groups divided by variability within groups, and we get the value 79, which is very high. If it is more than 2, we probably will get a statistically significant difference, very close to 2, 1.96 or so. This is 79, so that's why we get the p-value way less than 0.05. In fact, it is less than 0.0001. Okay, so here is the interpretation. There is a statistically significant effect of cholesterol status of diastolic blood pressure. So we know that cholesterol has a significant effect. Somebody who has high cholesterol is surely have an effect on his diastolic blood pressure. R square here is 0.03, very small, which means that only 3% variability in the diastolic blood pressure is accounted for by cholesterol. Small, but it is significant, meaning that cholesterol does affect your diastolic blood pressure, although only by a minute, not minute, but small, a small value, that is 3%. Okay. Let's move on to the next table, type 1 and type 3 sum of squares table. These are mainly interpreting that if there was equal variance across the groups, and the interpretation, because the p-value is less than 0.05, was that the variance was not equal across the cholesterol groups. Like t-test, ANOVA also assumes that there are equal variances among all the groups which are being compared, and this Levine's test just confirmed that they were not equally variant. The variance was not equal among all these groups. So in this case, a more appropriate test will be non-parametric test. The non-parametric test equivalent of ANOVA is Welch ANOVA, and luckily we also have the results from Welch ANOVA, which still confirms that there is a highly significant difference between the three groups with the desirable, borderline, and high cholesterol levels. Okay, and then this table 6 is for the descriptive statistics. We know that there were around 1,861 individuals who had borderline cholesterol, 1,405 had desirable cholesterol, and 1,791 had high cholesterol level. And here is their mean diastolic blood pressures: 85 for borderline, 82 for desirable, and we see high cholesterol level for those who had high diastolic blood pressure for those who had high cholesterol levels. I'm not going to go in the details of all of them, just jumping directly into the final interpretations. That is, the diastolic blood pressure is significantly associated with cholesterol status, which means that people with desirable cholesterol have lowest diastolic blood pressure, while those who had high cholesterol had highest diastolic blood pressure, and these differences were statistically significant. We did not paste here the visuals, which we can check directly in the SAS results. We see that the box plot for the borderline individuals is, for those who are desirable had the lowest set box plot. We can visually see that it is low. Borderline had slightly higher, and those who had high cholesterol, their box plot is even higher placed in this visual. And now here here SAS is comparing group to group. For example, this let me explain this. This oblique line is the statistically significant line. If any of these lines touches this line, it means that it is not statistically significant. And if it is not statistically significant, this SAS results will give that line in dark brown. But we see that the individuals with high cholesterol have statistically significant different diastolic blood pressure compared to borderline, and high also had statistically significantly different diastolic blood pressure from those with desirable cholesterol level. When we compare borderline, the individuals with borderline cholesterol, they were also statistically significantly different from that of the individuals with desirable cholesterol status. In case of N-way ANOVA, we are able to look at the difference in the continuous outcome when there are more than one uh, exposure or there are multiple covariates. Let's do it and then I will explain it from there. Under task and utilities, under my task, under linear models, search for N-way ANOVA and double click. Okay, and this will open up a new pan in the middle. The data set we're going to use is the same one. Under roles, under dependent variable, let's use diastolic blood pressure again. Now, next field, the factors. Now, it is giving us the option to choose more than one. Just click on the add button, the plus button here, and let's see if diastolic blood pressure differ when we have more than one exposure. Let it be BP, not the BP status, because we already have the dependent variable diastolics, weight status, and cholesterol status. Okay, what we are trying to determine here is that after adjusting for weight, is cholesterol status is still statistically significant when it comes to diastolic blood pressure? Is there is still an association if we have already adjusted for weight, or weight has after adjusting for cholesterol, is weight status associated with the diastolic blood pressure? Now move on to the next step, model. This is an important step here. Click on edit button. Choose both of your covariates, Control A, or you can just press and hold Control button and add. Click OK. And under Options tab, I'm going to keep all the default options. The only thing I'm going to change is the maximum number of plot points and submit the code. Okay, so now here are our results. Okay, the first table is simple. It is just giving us the groups within each of our covariates. For example, cholesterol status, we have borderline desirable and high. Weight status, normal weight, overweight, and underweight individuals. These are the number of observations which were read, and these were the numbers which were used because there were some missing values. And here are our F statistics. The model sum of squares, this error sum of squares, this degrees of freedom, this. And if we divide model sum of squares with the degrees of freedom 4, we get this value. And if we divide error sum of squares with the degrees of freedom, we get this values. And when we divide model sum of squares with error sum of squares, we get an F statistics, which is even higher than when we did it only with cholesterol status. And we know that if it is more than 2, the p-value is going to be less than 0.05, which is the case. In the next column, we see that it is even less than 0.0001. Now look at R. R is very important here. R has gone up. Previously it was only 3, but now we see that with weight status and cholesterol status both included, the R has gone up. Almost 10% of the variability in diastolic blood pressure is explained by weight and cholesterol status together. That's a pretty decent R for health sector. Next, it is calculating the p-value for the overall model, and we see that type 1 and type 3, both of them have below 0.05. In fact, it is less than 0.0001. The difference between type 1 and type 2 is that type 1 checks individually and type 3 sequentially. But in any case, both of them are 0.001, meaning that both these values contribute significantly to the diastolic blood pressure. Next visual is very cool. This is for the diastolic blood pressure for different weight status, factoring in the cholesterol status. For example, we see that those who were overweight individual, those who were overweight, they with the borderline cholesterol status, they still have higher diastolic blood pressure, and those with desirable cholesterol, they still have higher than normal and overweight individuals. And at the other end, we see that the overweight individuals still have high diastolic blood pressure even for those who have high cholesterol status. So it is in fact factoring in both our covariates into one model. And if we move down, it has more visuals. So for example, over here, we see that those with high cholesterol are statistically significantly different diastolic blood pressure than those of borderline, and statistically significantly different from those of desirable cholesterol level. I'm not going to explain the table for weight status, but one thing to note over here is that now, after adjusting for cholesterol status, we see that normal weight individuals have diastolic blood pressure, which is very close to the statistically significant line here, right? So it gives us some idea how two or more covariates can be linked to one outcome.